Okay, so I'll continue with control theory today. We'll start with a discussion of some other constraints on any control system, any feedback control system. Linearity, measurement error, robustness, in addition to the three we discussed earlier. And then really this is sort of the heart of control theory, classical control theory, which is called PID control. So P stands for proportional mode, I is integral mode, D is difference mode. And I'll see how much we'll get through with PID. We'll certainly do P, and hopefully we'll get through I and D as well. A good understanding of PID control means that you can actually go out and build a control system. Okay, understanding what the different gain parameters are. You can go and buy a PID controller. You can go to the store, buy a PID controller, attach it to a system, make it a control system. It's pretty much as simple as that. And just understanding what these knobs mean for the P and the I and the D will really help you build practical control systems. And there are many controllers out there which are just out of the box PID controllers. So if you have a control problem, what you'll probably do is try PID control just to start with, because that usually works. And if it doesn't, then you spend some more time. So this is really at the heart of things. And then this will be the basis for understanding more advanced concepts, which you'll hopefully get to Friday, and then into state-space control, or what's called modern control, which you'll study next week. So anyway, that's just a preview of what's happening. Let me start with this issue of linearity. So linearity is an assumption that you're making in design of a control system. We're assuming that the plant and the controllers are both linear, so that we can apply, we can assume that it will be linear LTI, linear time invariant, and then we can actually use all our transforms, etc. Of course, linearity is not going to be true. We've already discussed one reason why linearity is not going to be true, and that's because we never have the output proportional to input for all values of the input. Okay, there's always going to be saturation going on, so that at some value of input it's going to be saturated. You cannot, the system is physically unable to respond proportionally. So there's going to be a max. Okay, saturation means that, so linear means that, okay, in some sense, if you have some value x, the output y is going to be linear all the time. But saturation means that basically at some point you just have a cutoff. It doesn't go beyond that, whatever it is, right? So if you have a buffer, you can say if I increase the rate a little bit, the buffer fills up a bit faster. But when the buffer is full, I can't fill it up anymore. So obviously I get a saturation. And this is going to be true in all cases. So linearity is not going to be true because of saturation. And this is true for all physical real systems. The second reason for non-linearity is because of degradation. So by degradation, this is true mostly for mechanical systems, where essentially things become loose. Okay, your bicycle is going fine after 5 years, 10 years. You know, you turn the handlebar, this wheel doesn't turn right away. There's a little bit of play. Okay, and this is because of natural wear and tear. Okay, this happens for mechanical systems, chemical systems, you name it. After a while, things basically go out of tune, and so it's not linear. And you usually have to worry about that as well, because you can't just pretend that it's not there. So when I talk about robust control in a minute, we'll talk about degradation in a little bit. But the one thing to keep in mind about linearity is to be explicit about nonlinearity. Explicitly deal in other words, you want to recognize saturation. So you say, okay, I'm assuming I'm doing linear stuff, but just in case there's saturation, just in case I'm in this upper or lower saturation bound, I'm going to do something, okay, which is going to get me out of saturation. How do we do this? Well, remember this. If you remember this graph over here, we have some input and some output, and the output is saturating at some point over here. Now, what you want to do is to say, if my output is in this range, Okay, that's sort of the forbidden zone. If it's in this range, I'm going to take some control action which is going to get me out of that range. I'm going to dramatically reduce the input back so that I'm getting out of this zone back into the linear zone again. Okay. To give you an example of this, if you remember what TCP was doing was that you keep increasing your rate, and what happens is your buffer is going up, but actually when you're in linear zone, you don't know what's happening. What then happens is you eventually fill up the buffer, so your rate keeps increasing, you fill up the buffer, you have packet loss. When you have packet loss, you say, oops, I'm in the saturation regime, I'd better reduce my input rate, and so you reduce your input rate. Okay, and then you do this again. So what TCP is doing actually is to put the system into saturation and out of it, or again, because the operating point it wants to be at is exactly at the boundary of saturation. Yes, your question? Oh, okay. So this is what's going on at TCP, and this is what you want to do with other systems as well. Yeah?
I was wondering, when there is a saturation level for the rate,
Yeah. Yeah.
why does it have to come back all the way down? You can just limit the rate at that point itself.
Sure, that's because of delay. What happens is that I've sent these packets out already, and they're on the wire, so to speak, and I already sent them too fast. So by going slower than the actual rate, it compensates for the delay. If there had been zero delay, then of course you don't need to do that. You'd get immediate instantaneous feedback, but in practice you don't have that. So you're going to have to go lower in long enough so that you compensate for the excess stuff you sent out earlier. That's a good question. I mean, so that's how you compensate for delays in the control loop. But this is what's going on. So the other case is whenever you have a computer network or you have something with a buffer in it, what you want to do is to recognize when the buffer overflows. Okay, packet loss happens or buffer saturation happens. That's a sign that something really bad is going on, and what you want to do is to back off, really back off a lot. And so you put a special rule that says, look, this is my linear control zone. This is where I do my nice control theory stuff. But when I get into this zone, I'm going to get into saturation, or in computer networks it's also called congestion. And when I'm in the congestion zone, then I'm going to actually take some dramatic control actions to reduce the load. Okay. Similar situation is the electrical grid. When you have loads that are high, and let's say it's a hot summer's day, everybody has the AC on, that's a very high load because air conditioning takes a lot of energy. When you have very high load, what happens is the system becomes actually nonlinear. Well, it's nonlinear to begin with, but it becomes close to collapse. You can have cascaded collapse. So you do blackout. You just say, okay, this section, I'm not going to supply you energy, you guys can all sweat. Okay. And that's what happens. It's a rolling blackout. It's a blackout where each section, you choose any particular industry. You say, okay, all chemical plants are going to be turned off, or your particular geographical region, you turn off electricity because you're in the saturation or congestion zone. So again, that's an example of where the system is protecting itself and getting back into linear, good operating zone by doing special rules. Okay, are there any questions about this? So the takeaway message is put in a special rule so that you deal with nonlinearity. Okay, so let me talk about measurement error. So the measurements are susceptible to two kinds of errors. And the first kind of measurement error is essentially an offset error. So for example, if you have a house that's being heated or cooled, you set the thermostat to 23 degrees, actually it's 25 degrees. So it's always going to be 2 degrees off because the control system is very happily going to keep you at whatever the reading is, but it's 2 degrees off, so everything is off. And so when you have that kind of error, you can't compensate for it. No feedback system can compensate for measurement errors, if you have offset error. The second kind of error is a delay, and delays are actually really, really difficult to deal with. In the classical control system, or any control system, delays are a pain in the neck because you do some action and you know what happened as a result of the action. So you give the input to it, but you know what happened to it, or the measurement takes some while before you get to it. So what do you do in the intermediate time, right? Let's say you set the control value to be something, and then the output, you don't know what the output is, what the response is for some period of time. So you have this unknown time, right? You're kind of sitting there waiting, well, I don't know what happened. So you have to do something, right? If you keep doing something and that something is wrong, you're injecting bad stuff into the system. You're maybe sending too fast or too slow or doing the wrong thing, whatever it is. Let's take a case of a boiler which wants to keep the water at a particular temperature. Let's say at boil water, so you keep it at some particular temperature, 100 degrees. And let's say that what you do is you have a coil and you heat it, and then you let go when it's hot enough. So if you have a measurement delay, you heat the water, and then while it's being measured, let's say it's delayed by 1 minute. For that 1 minute, you may be too hot or too cold. If it's too cold, you're going below the set point. If it's too hot, you went too high, and then you have to say, okay, how much time do I need to turn it off longer to compensate for this mistake? And the delays may be variable, and so then you get into really complicated problem. So if you have a delay and if you have variable delay, the short answer is that we really don't have good solutions to this. Okay, and so the best way to deal with it, and I'll discuss this later when we talk about advanced control concepts, the best way to deal with this is to predict what the future is going to be based on what happened now. So you say, okay, I'm seeing this measurement trend. I am predicting that 30 seconds from now it's going to look like this. And based on that, you're going to take control action. And if your predictor is good enough, you're okay. And if it's not good, you have trouble. Okay. And so you get into oscillations and things like that. And but you can't. So there aren't good solutions. I'll talk about some sort of mathematical approaches to these in a bit. But you should be aware of the fact that delays are going to cause problems. Again, to take my bicycle example, because the bicycle is a good example of a control system because you have to stay on. Imagine that when you turn the bike handle, it takes 2 minutes before it actually turns. So you turn the handlebar, or take a car. If you're driving a car, you turn the steering wheel, and then 2 minutes later, it's actually going to turn. And for that 2 minutes, you're still going on that same course. So the road is turning, okay? And so instead of turning it right away, you have to, in advance, start turning the wheel, okay? And it's kind of crazy. You turn the wheel, and then, because you're predicting that over there, you're going to be that far away in the future, and then you'll need to turn the wheel at that point in time. Either that, or you go very, very, very slow, and you turn the wheel a little bit, and then you go super slow, right? Either way, it's not much fun, okay? So if you want to mess up somebody's video game, just introduce a 1 to 5 second delay into the video game controller, and watch the fun, because they'll turn the thing, and there's going to be a lag. And then the character, whatever, Super Mario Brothers, my daughter plays Super Mario Brothers. So here's the monster coming, and you say jump, and the monster eats you up before you can jump. So what happens is you're going to have to compensate for that and jump too soon. Your brain really can't deal with that very well, and neither can the controller. Okay, so that's measurement error. And the third thing I wanted to talk about is robustness. So robustness is our way of dealing with these nonlinearity and measurement errors. We'd like a system to be robust. And robustness means that, okay, we actually don't know the system very well. We don't really know the parameters. There may be delays. There may be measurement offsets. We still want it to work fine. And so robust control is basically to insensitivity to bounded variations. So it's bounded, it's not unbounded. Bounded variations in the system parameters. And this is a huge area of research. In fact, you can find many textbooks just on robust control. So if you understand a little bit of control, you can say, okay, how to do robust control, and it's a lot more work, okay, to do robust control. So you can do control. To do robust control is much harder. So I won't go into it other than saying, okay, if you really want to build a practical control system, you probably want to take robustness into account and look and investigate robust control. Okay. So these were the issues. So we talked about 3 other issues previous time: disturbance rejection, transient response, and stability. And then these are the 3 other issues. So we have sort of 6 issues that you want to keep in mind in designing any control system. So you want it to be stable, you want the transient response to be nice, so even though when disturbance comes in, we're not doing something crazy when the disturbance comes in, because there will be disturbances. And you want to worry about the rejection of the disturbances. And then we want to have the system to be linear, or at least be careful to do something when it goes non-linear. We want to be cognizant of measurement errors, and we want the whole thing to be robust. So these are kind of issues which are true for any control system, any practical control system. You need to worry about it. Okay. Any questions on this so far? Okay, so I'm going to kind of move on to the central part, which is PID control. So let me first set the stage for the PID control, and then I'll go into the different modes for that. So I've been referring sort of on and off to classical control and modern control, and there is actually a big distinction between the two. Classical control is roughly what was done in the 1920s, and one of the main drivers for classical control was anti-aircraft guns. Okay, anti-aircraft guns for during and after the First World War, because airplanes or bombs dropped from airplanes came into the picture in around the 1917, 1920, something like that, and anti-aircraft guns were invented. And the anti-aircraft guns, as you have ever seen, are very big. Okay, they're maybe half the length of this room over here, very heavy, and they're on these rotating pedestals, and you steer them when you shoot at the planes. Okay, obviously it's in the interests of the designer of the anti-aircraft gun so that you hit the plane, but it's a complicated problem because of many reasons. One is that there's a lot of inertia, so if you move it, it keeps moving. So if the plane is moving like this, the plane is trying to take evasive action, the plane is moving fast, the aircraft, the platform is moving fast. So it's a very complicated control problem, let's put it like that. And that led to the military spending a lot of money into essentially investigating how to control these things in a robust way. You could not have a human do it, okay, because of delays, in part because it was just too many variables to take into account. And these ideas of PID control and so on were I guess put into place, and then they were also used for controlling chemical plants and things like that, where the same ideas, the same mathematics held true. PID control became quite popular, widely used, still used today. And in the 50s, however, people realized that it was not good in dealing with multiple input, multiple output systems, and you have multiple control inputs, control outputs, especially because we couldn't use transfer functions for dealing with MIMO systems. And so for dealing with multiple input, multiple output MIMO systems, they decided to come up with essentially state space control, where you have a state vector, multiple inputs, and as you saw mathematically, it's easy to represent MIMO using state vectors. And that really went straight into a matrix using advanced linear algebraic techniques. So it was all based on linear algebra and matrices. So in terms of how to explain control theory, I was kind of decided to, whether to go with modern or to classical. And the way I see it, PID control or classical control is very intuitive. You can kind of get a good understanding of this. Once you do that, modern control actually becomes more comprehensible, whereas if I show you modern control right away, you'll just see a bunch of matrix equations and there's no understanding what's going on. Okay, it's very hard to deal with concepts like stability and delay and so on in an intuitive way. And here, the emphasis is really on intuition. This is not a course on control theory. It's a course that's trying to give you a glimpse of what it's like, enough so that if you go pick up a textbook on modern control, you know what you're doing. Okay, at least you have some idea what it's talking about. So we're going to start with PID control with the explicit recognition that the goal is to develop intuition, and that this intuition will be used in doing in studying modern control, which we'll come to later. So let me just draw one figure, and then we'll take a break. So the figure I want to draw is the same old figure. I have the plant, and again remember it's called GS. Is in the G of S is in the Laplace domain. We have the output Y of S. We have the feedback, and we'll assume it's a unity feedback. So H of S is equal to 1, and we have a controller. And the controller is the D, and over here we have U, and the controller acts on the error E, which is the negative of, sorry, I should have U, and then I have the disturbance W, and the error is the difference between the command R subtracted from the feedback value B. Okay, so this is sort of your standard feedback control system with a command R, disturbance W, output Y, and with the feedback, let's say unity feedback, H equals 1. In proportional mode, PID all talks about this part over here. Okay, so here we have E, and so in the case of the proportional mode, we're going to basically say U equals some K times E. Okay, and this is going to be, and we call it KP. In the case of an integral mode, U equals Ki for integral E, and we divide by S because that's what integral basically means. We're going to divide by S in the Laplace domain, and this is the P, this is I, and for the D, U equals KD SKDE. Okay, or in the time domain, basically U equals KPET. In this case, U equals KI integral ET dt, and then U equals KD dE by dt. Okay, so that's the time domain and Laplace domain. And so all we're really saying is we have some error signal E, and this output U is linked to this error signal E using one of these three equations. So it's really as simple as it gets. It's just a constant multiplying the error, the derivative of the integral of the error, or the derivative of the error. Okay, and so we'll study what that means in just a minute. Let me take a break, and then we'll continue with that. Okay, so let me start with proportional mode control. So in proportional mode control, we have the U equals this. So we have U equals KPE, and so U equals, or I should be more precise, US equals KP, a constant, E of S. And the issue here is that so I want to talk about two things. One is this is the loop gain, and the other thing I want to talk about is the droop. Okay, so loop gain is basically the proportionality factor. Okay, so you have some error, let's say some certain amount of error. How much you magnify it by or diminish it by? It's linear scaling, and that's Kp. So if you take a very large control action, because U is the control action based on a small amount of error, then you have a high loop gain, so you're being very sensitive, right? On the other hand, if you reduce Kp, you're not being very sensitive. So if you buy a PID controller and say set Kp, what that means is, okay, I'm going to have certain amount of error. How much do you want to respond to it? Do you want to respond with a large response or a small response? So when you tune the controller, what you do is you choose a large Kp, and you kind of diminish it, and you say, oh, it's too responsive, I'm going to tune it down. So it's a very simple control knob. If you find the response, it's too responsive, it's oscillating, for example, turn it down, right? And an example of, we already seen what error looks like when you're steering a car, for example, and you have let's say you're doing speed control. So the error is the difference between the desired speed and the actual speed. Let's say the error is 2 kilometers an hour. Do you reduce your brake? So do you step down hard on the brake, or do you step down lightly on the brake, or do you remove the foot on the accelerator very fast or just a little bit? That's U. Okay, same thing. If you see you have a curve, and you're very far away from the midpoint, do you sharply turn the steering wheel or do you do this a little bit? That's loop gain. Okay. Now, the greater the loop gain, what happens is that the more responsive the system becomes, but even the smallest amount of delay is going to make it unstable. Okay. So you have to be very careful to balance the loop gain from the responsiveness and the stability. So there's again the same old trade-off. More responsiveness, less stability. Okay. Now in the actual math I'm going to show you in just a minute, we won't actually see this because we're assuming delay is 0. Once you introduce delay, the math becomes very difficult, so we're not going to do that. But in practice, you will kind of reduce the loop gain down so that you have stability, or at least your oscillations die down. Droop is means that it's very simple to see that if the error is 0, the control action is 0. Okay. The error is 0, control action is 0, which means that in some cases we need some control action to be present. Okay. And so in this case, what happens is that we will maintain a persistent error just enough so that we have some control action. Okay, so we don't have 0 control action. Okay. Now 0 is sort of a funny term because we kind of we can choose 0 arbitrarily. Okay, and we can say this is my 0 accelerated position, this is my 0 speed, etc. But again, I'm generalizing and saying that in cases where we need some control action all the time, then those systems will have a persistent error, which is a droop, and it's called the droop. And now if you have very high loop gain, then the droop will be small, because even a small amount of error will allow us to give a sufficiently large control action. And so the loop gain being high basically is going to compensate for the droop. Okay. But typically there will be some persistent error. Okay, so to explain control mode a little bit more, I'm going to actually solve the I'm going to first solve the web server example, and then I'll do the homework example, so you'll get 2 examples. So let's start with the web server example. And here what happens is that we have a plant whose Laplace transform is just 1 over s, so it's a very straightforward Laplace transform. And we're going to have some output y, which is the buffer occupancy. And so for the case of the web server, it's convenient to write u equals r minus y over tau, where tau is the gain. So I've written the gain not in this fashion, but in a slightly different way, where r is my reference input, y is the output. So this is r, okay, and this is going to be r minus y, okay, and so u is going to be, I'm writing u, it's my green, I'm writing u over here as, instead of kp times r minus y, I'm just writing it as 1 over tau r minus y, because the physical interpretation of this is a bit easier to see, because r is essentially, in this case, my, so r is the reference rate I want to be at, and so let me see, the r is the reference set point value, the buffer set point value. Okay, so I'm saying I want the buffer to be at, let's say, 5 packets. That's my desired set point. If you remember, I'm choosing this value so that the system is able to use any unanticipated increases in capacity because of the disturbance. So I have some buffer set point value r, and then I have some actual set point value, which is y. So the actual buffer value is y. Okay, so now r minus y becomes the error, and it tells you how far away you are from the desired set point. So if I have a set point, if I have a buffer like this, okay, and I want the set point to be here, I can be above it, so this would be y, and this is r. So in this case, I'm above the desired set point. R minus y is negative. And if I'm below, I'm over here, then this would be y, and then r minus y is positive. So when r minus y is negative, what do I need to do? I need to lower my ascending rate, right? U is my control. Over here, I want to lower my sending rate. And when it's below, I want to increase my sending rate. By how much? The meaning of tau over here is I want the buffer set point to reach the desired output value R in the absence of disturbance after time tau. Okay? Because you see, I don't want it to happen instantaneously. Okay? If I want instantaneously, they'll just set tau to 0, right? But I want that the output should reach the output should reach the desired value of the set point after the time period tau. That's the intuitive meaning of what's going on here. So you're saying, okay, things are bad right now, okay, because I have an error, but I want to compensate for the error after so much time. And that's the meaning of Kp. In this case, Kp, the loop gain, has the meaning of how far in the future are you willing to wait for the output to reach the desired value. Okay, do you want it to be right away? Do you want it much further away? If you're willing to compensate for the error over a longer period of time, tau is larger, Kp is smaller. Tau is larger, Kp is smaller. If you want to do it right away, tau is smaller, Kp is larger. So I use tau, 1 over tau as Kp, just because I want to illustrate that there is this notion of time, and it's a very intuitive and natural way to express this particular system. So the web server has got a certain number of packets in the buffer, and what I want to do is I want to get to the target after time tau in the absence of any further disturbance. Of course, there will be further disturbance. Of course, by the time tau, in time tau, other things will happen. That's okay. I'm always trying to get there at this point in the future. Okay, that's the goal. Always when I get to the future, if by any miracle the disturbances go away, I will get there. Okay, and in computer science we call this eventual convergence. Okay, eventual convergence is the term that's used in distributed systems. In the absence of any further input changes, whatever, the system will converge to the desired value. In control theory, we basically say that the loop gain is over here, is controlling the point at which you're going to get quote unquote eventual convergence. Okay, so this is the intuitive meaning over here. Any questions about this? So all that is hidden in this very simple equation: U equals R minus Y over tau. Yeah.
What I'm not sure is like when after time tau, when R is equal to Y.
Yeah.
Sorry, when
R should be equal to Y at tau if there is no other disturbance. Yeah.
So in that case, it is 0, and the input becomes 0, right?
Yes. At this point, input will become 0 because error will go to 0. Correct.
Yeah. So in that case, output becomes 0 again.
The output will be the output will be so at this point. Yeah. The output is going to be. Remember, output is the buffer set point value. It's not the rate. The output is the buffer value. See, Y is the buffer value. It's not U.
Y should be the actual buffer size at that particular.
That's correct. Yeah, the buffer occupancy value maybe is what I should. Instead of calling it buffer value, let me call it buffer occupancy. That's more accurate anyway.
In the case like when input is 0,
right.
The buffer occupancy tends to go to 0. Right?
That's correct, but that's not good. We want the buffer occupancy to be R. R is a reference set point.
So what does that mean? Like the after time tau when R is equal to Y,
Yeah.
error becomes 0, and then
Error becomes 0. That's what you want, right? You want if the buffer is at the right set point there.
in this implementation, when the error becomes 0, the output Y also becomes 0.
No, the output Y is not 0. Then the output Y equals R. When the Y is equal to R, your U equals 0. If your buffer is the right set point value, then you don't need to send any more data, basically. But of course, the disturbance is the draining of the buffer. Remember, in this modeling, the service is disturbance. We don't know what it is. So we're always going to have disturbance just by the fact that the plant is doing some work. It's being modeled as a disturbance. If the web server stops doing any work, it's just gone on strike, it's not doing any work, right? And you're at the set point, then that's true. You won't give it any additional work because, see, look, I have 5 packets in the buffer already. So then you're fine. Yeah. Okay. Any other questions? That's a good point. I mean, you have to be careful that Y equals R is the desired set point, not Y equals 0. Okay, so with this equation then, we can actually make very quick progress because we know that Y equals 1 over S, okay, U minus W, because Well, the plant is 1 over S, and